Everyone. This is our second press conference of the day, and it's on sea ice decline in the Arctic. And we have three panelists. Alexandra Jan is an assistant professor at the Department for Atmospheric and Oceanic Sciences at CU Boulder in Colorado in the US. Marcel Nicolaus is a sea ice physicist at the Alfred Wegener Institute for Polar and Marine Research in Germany. And Mikhail Dobrinin is a research scientist at the Center for Earth System Research and Sustainability at the University of Hamburg. And our speakers will give their talks, and following that, we'll open the floor for questions. Thank you. You can start.
Okay, thank you. So I'm going to talk about internal versus forced Arctic sea ice variability and the components in the sea ice loss that we've seen. I'm coming to that from the perspective of a climate modeler looking particular at Arctic sea ice. And so what is this internal variability that I mentioned here? So that's the variability that's inherent to the climate system. So even if we didn't have any forcing on the climate system from greenhouse gases or over long time scales from changes in solar forcing, we never would have the same climate every year or every decade. We have some internal variability in the system. For example, these large modes of variability that you might have heard of, like the North Atlantic Oscillation. And so we can clearly see that in the observed sea ice decline in the Arctic, which is shown in this figure over here. I don't know if I can point, but it's showing the Arctic's sea ice extent since the start of the satellite record in 1979. And you can see that over time, overall, obviously the Arctic sea ice has declined in September when we see the minimum sea ice extent in the Arctic. But we see a lot of variability in that decline. So that's, if we just look at the black line, it goes up and down from year to year. And rarely do we see 2 years that have exactly the same sea ice extent. And if we compare the amount of loss of Arctic sea ice in the summer that we've seen, which was about 3.5 million square kilometer between the start of the satellite record in 1979 and the minimum sea ice extent that we've seen so far, which occurred in 2012, that was about 3.5 million square kilometers. And just to put that in sense of scale, since that's a really big number, that's all the western states in the United States that are colored in here as red. So it's a really huge area. And it's almost as large as the remaining sea ice that we still have in the Arctic in September, or it had in that 1 year of minimum extent. And then the recovery that we saw up until from 2012 to 2013 was about 1.7 million square kilometers. So almost half of that loss. The next year, we had more aerial coverage again, and that's this effect of the internal variability. That was not something that's forced by greenhouse gases or any other natural forcing. It's just due to these internal variabilities, changes in the weather patterns that we have in that specific summer leading to the sea ice. And so if we look at the area of that, that's a really large area shown here in the yellow color. And so that's so then if we look at climate model simulations of sea ice extent, we can clearly see that large impact of internal variability, and we can differentiate the forced response from that internal variability. So what I'm showing here is some model results from a large ensemble that we have from the Community Earth System Climate Model, which is a model developed in the United States. And we have 40 different realizations from that model with exactly the same model and the same forcing. Here we're using the strong emission scenario for the 21st century. And we can, if I flip through a couple of these, I don't have all 40, but if you look at the blue line, we can see that they have very different interannual changes, and even on decadal or multi-decadal timescales, they vary a lot, but they all have in common that we overall see a decline in sea ice extent over time. So if we look at all 40, you can clearly see that forced response there. They're all declining over the 21st century and reaching ice-free conditions sometime in the middle of the 21st century. But if we look at the individual members, some of them are showing a later, larger sea ice loss, sometimes very rapid ice loss events. Some show these periods of almost constant sea ice for up to a decade with rapid losses afterwards. And some show somewhat more of a gradual decline with ups and downs that are similar to what we've been observing so far in the record. So the observations in the real world are kind of like one of these ensemble members, and we can't really predict based on just the forcing that we're expecting to see over the 21st century which track we're going to be on. All of these kind of match the observations relatively well. They're all from the same model, so it's capturing the physical parameters or the physical mechanisms in the system, but we can see that just due to internal variability, we can get a large change. We can use these models also to understand the forced response though. So if we look at the trends that we've seen in the observational record, we can split it out into how much of, to see whether there actually is a forced sea ice decline or if it's all just due to internal variability. And we can clearly attribute it to some forced response. Here what we're seeing are the trends for 35 years in these model simulations in unforced pre-industrial climate where we don't have the greenhouse gases that we have today in the atmosphere, and we can see that in the black. So we can get, due to natural variability, about trends of plus or minus 0.5 square kilometers per decade. And then if we look at the most recent period where we have the satellite observations, 1979 to 2013, we can see that this trend distribution is clearly shifted towards negative trends. So this negative trend that we've been observing clearly has that forced component from the greenhouse gases in the atmosphere, and we can't get that just without if we have simulations that don't have that greenhouse gas. And you can see the model is capturing the observed trend, which is shown here as the one red dot from 1979 to 2013. So if we kind of just summarize what we can attribute to forced versus internal variability based on model results, we clearly can see that as a result of climate forcing, we have a negative CSX trend since 1979. It's not just due to internal variability. And the models tell us that we will see a continued sea ice decline in the future due to greenhouse gas forcing. And then also if we look back in time, there are periods where we can clearly see a forced response of the system with more sea ice during the Little Ice Age, which occurred in Europe between 1450 and 1850, and with less sea ice during a warmer period that preceded the medieval climate anomaly. Again, we can use these model simulations to show that this is not just something that happened due to internal variability, but due to forced response. But the internal variability really determines the magnitude of the sea ice decline since 1979, and the model results suggests that between 30 and 50% of the observed decline might be due to internal variability. The internal variability also clearly determines the magnitude of the future sea ice decline on yearly to decadal timescales. If we look at 100 years, we have the forced response, sea ice will decline and most likely disappear during the 21st century under the strong emission scenario, which is the track that we're on right now. But even on decadal timescales, internal variability makes a prediction of the exact path that we're taking to this ice-free condition, and the timing of that very difficult. So I'll be happy to answer any questions afterwards on climate modeling of Arctic sea ice. Thanks.
Good. Yes. Thank you for inviting me for the press conference. Welcome, everybody. So my name is Marcel Nikolaus. I'm working in the sea ice physics of the Alfred Wegener Institute, and we are looking now more from the observational side to the changes in Arctic sea ice. And I would like to summarize points from two kinds of observations. From autonomous platforms called buoys that kind of alarmed us, and then how we looked into the cryosat satellite data. So we developed these kind of autonomous platforms that we installed on the sea ice a couple of years ago, and we deployed them on Arctic and Antarctic sea ice. And what they do measure, they measure snow depth and air temperature in the Arctic, because those are two very important variables. It was originally designed as a snow buoy only, but we have this air temperature, and especially the last winter, we realized how important that air temperature measurement was. What we did is, on a Polarstern expedition into the Arctic sea ice in September, October last autumn, we deployed 7 of these buoys, and you can see them as the color lines in the plot. So where the plot started, we deployed them. Somewhere in the middle, they were at the end of December, and the dot at the end is the position from last week. So with that, we covered quite a bit of an area over the Arctic Ocean. And here I will now focus on the air temperature on the next slide, because what we saw is that end of December, a very strong increase, even above 0 degrees centigrade, was measured from the buoys. So, and this is certainly some 20 to 40 degrees higher than what you usually expect. So melting surface conditions in the Arctic is quite remarkable. And when I was in the Christmas holidays, I just saw the news myself that it was so warm, and I was wondering where it came from. But our buoys, they report into the global telecommunication system, and with that into other data portals and into weather forecast models, and that's where they picked up these measurements to force their models with. And that was exactly these units. And that made us very curious. So what would have that impact be? Now we can see the snow depth over the time series. Unfortunately, only 5 of the 7 buoys because 2 didn't work that well. And what we see is all these dots from early October to now end of March, they have rather variable but increasing to constant snow covers. Only one of the 5 shows a decrease, the yellow one, of some 10 centimeters. So the Arctic was pretty warm, but we do not see a surface melt. We do not see that the snow melted away completely, or even the sea ice melted, made it thinner. But obviously it is very warm. And that then motivated us to look into our satellite data of sea ice thickness. So we use Cryosat-2, that's an ESA satellite in orbit right now since 2010. We look into monthly data from the satellite on 25-kilometer resolution. That gives us a coverage of the entire Arctic in terms of sea ice thickness of the Arctic. And if we look into, if we start that story in November last year, so end of summer or into autumn, we saw that the ice was already thinner than in the year before. So on these maps, you have the left-hand side is 2014, the right-hand side 2015, and the reddish colors are the thinner ice, and the yellow colors, the bright colors, are the thick ice. And you see the thick ice north of Canada, Greenland, where you would expect it. But if you take the difference of the two, we see that the area coverage was not very, very different. There was a difference, but not too much. But the ice was quite significantly lower, thinner. And then we go through winter, and now we look into the March maps. I have now this year's March top right, 2016, but also the previous years. And what was striking to us is that the ice thickness distribution in this spring now, or end of the winter, is very similar to what we had in the year 2012, which is, if you remember, the preceding record minimum in summer, September 2012. So the ice is much thicker than in the thinner, excuse me, it's much thinner in 2016 now than in the 3 years in between. Where did that ice change? This is a difference map, and we can see that the ice got thinner most over the Arctic, especially in the Beaufort Sea and the Kara Sea, etc., except one line or area north of Fram Strait, so the Atlantic Ocean part, where it got thicker. We think that the thickening is mostly due to dynamic effects, where ice got pushed more together. But the alarming thing here is that this ice will most likely be exported over the summer now, because this is the area that during spring and summer will leave the Arctic into the North Atlantic and melt there. So, and with that, we have now 3 reasons. We had thinner ice in the autumn, we had less freezing in the winter, and we have this high likeliness of export of sea ice for the next months to come. As I said, we talked about thickness so far. If we now combine with what we heard about before with the area, this graph gives you the volume. In order to work on volume, we also have to include ice thickness from other satellites, in that case from the SMOS satellite provided by the University of Hamburg in that project. And if we combine that, we can come up with volume estimates. And if we look into these graphs on the left-hand side, we can see how the volume increases. And if we focus on the green line, this is 2015-16, the winter, then we see that we are very close to the line which is more purple from 2011-12, preceding the year before, and much lower in the ice volume, so area times thickness, than in the preceding years. To look more into details, I would like to invite you to the poster of my colleagues Robert Rickert and Stefan Hendricks about the Cryosat and also other sea ice thickness data sets that are available to judge these things. All these data are available through our portal as data for people who want to work with, but also as commented expert statements on the data of the sea ice portal. And I have a talk more on the snow buoy issue at 2:30. So I summarize my comments with this slide. So we do see a thinner sea ice cover than in previous years, some 15% less than in the last year, based on the volume. And I think the volume is very important, not only the area. We saw the strong summer melt 2015. We saw a low ice growth rate over winter, but we did not see any significant surface melt over winter. And if you project that now, and I don't want to say this is a forecast, but if you project that, we expect conditions that might be similar to 2020, to 2012. But we have to be aware that there are high uncertainties because much of that story, how the sea ice will develop, is decided now in spring and summer, depending on temperatures, on atmospheric conditions, on storms, etc. in the Arctic. So we will see. Thank you.
Let's see how we move that. It's on the desktop.
Sorry?
It's on the desktop.
Yeah, we can view full screen. Oh, sorry, no, that was wrong again.
We can do it once again. Yeah?
Excuse me, please. So I have to open the right one and now do the same. Full screen mode.
Yeah, thank you.
So, do you want us to, should we just?
Yes, we can shift it. Or you can click.
Oh, I can click.
Yeah,
If you
okay.
just give me the sign, I just click.
So hello everyone, my name is Mikael Dobrynin. I'm working at the University of Hamburg. I'm oceanographer and working most of the time with numerical models. So I'm using Earth system models, and the major part of the research is the ocean waves and the ice and the interaction. So not yet. I'm going now to highlight some topics that is related to the consequences of the decline of the ice extent in the Arctic. And this photo you can see here, it's a Barents Sea 2014. And that is how it looks like if the waves are going from the North Atlantic, and that is the result of the ice breaking due to waves. So my highlight topic is now that we will have some new wave system in the Arctic because of the ice extent is going back. As I said, we have here some climate projections based on the Earth system models, and you can see on this plot two lines. That is the coverage in percent of the area covered by the ice in the polar region, and the blue line is for the historical period for the climate as now, and the red one is the projections for the future climate based on the RCP 8.5 scenario from the last IPCC report. And what you see here is the seasonal cycle of the ice coverage, and you can recognize that in the future, by the end of this century, we will have the summertime extended up to 7 months, and in this time we don't have practically any ice at all in the Arctic. So that means we will have new conditions, a new wind and more open waters in the Arctic, and that is conditions where we can expect the increase of the wave heights and development of the waves on the Arctic, on the surface in the Arctic Ocean. So we do some experiments with the models, and this plot, it's an illustration how it can change in the future. So you see on the left side the September for the climate is now, and on the right side it's September and averaged values for September for the future climate. And the colors are for the wave height, and you can see that the Arctic has a strong impact going from the North Atlantic, and the waves from the North Atlantic are propagating up to the North Pole in the future. So on the other hand, we can also recognize some new wave systems that is related to the local change of the wind, and because we don't have ice as a limiting factor for the development of the waves, we will expect a relative high wave height in the sector of the Arctic that is closer to the Pacific. So the consequence for the Arctic that can be that the completely new wave system, it's also some additional force for the shallow Arctic and the coastal line. And a lot of segments on the coastal line in the Arctic looks like that one. It's you can recognize that is mainly consists of the ice, and it is also has a lot of organic matters and also the greenhouse gases. And in the lower part of this cliff, you can see that the effect of the water, basically, that is the effect what is going probably due to tidal and wave forcing. And we can imagine that if we will increase the sea level height and also the waves are going to be bigger, we can expect some more erosion from due to waves on the coastal line. And we can also try to simulate this situation, and so as an indicator for the additional force in the shallow region and the coastal line, we calculate so-called shear stress, and that is the force that is additionally going to make some impact on the seabed due to waves. And you can compare here also two plots, left to right. It's the historical period and the future period, the future climate. And you can see that in the historical period, the blue area is very close to the coastal. That means that it's not at all any impacts from the waves. But if we remove ice in the future, we do have some bigger waves, and even if it's with not huge differences between the wave height on the coastal between the historical and future climate, we will have more time that waves can impact the coastal region, and that leads to the possibility that the coastal line will be eroded quickly as a historical period, and the erosion rate of the coastal line can be accelerated due to waves. And finally, you can see here some references if you need some more details. And I would like also to invite you to our poster session today, and I will present a poster about the consequences of the changes of the forcing factors in the future climate for the shallow water and coastal line erosion in the Arctic. Thank you very much.
Thank you very much for your presentations. We'll now open the floor for questions. Does anyone want to ask any questions?
Jonathan Amos, BBC. Marcel, in terms of area, they called a minimum maximum record this year. In terms of thickness, volume, are you able to say whether in the Cryosat series we've seen a minimum, maximum? You know what I mean, this winter?
Yes, I think from so if we take the minimum of the maximum you just mentioned from the extent, and we also see the minimum in the ice thickness for March now. If you put that together, I think we haven't had as little ice in March in the Arctic as now in 2016.
Right, so this is a record in terms, are you saying this is
in terms of volume, this is a record.
This is a volume.
Yeah, a volume low record.
Yeah.
In the maximum time.
Yeah, absolutely, yeah. I'm going to come to the posters a bit later, but can you talk about a little bit about being able to see thickness in the Antarctic? This is something quite new, isn't it? And I know Robert Ricker has a poster on this because it was always used to be said that you would struggle to get thickness in the Antarctic because of the amount of snow acting on thin ice, pushing you wouldn't get a freeboard, you get a negative freeboard in essence. So are we saying that we're starting to solve that problem?
I mean, I can say we're working on it, but you're exactly right. So the snow makes a lot of the story in the Arctic and in the Antarctic. In the Arctic, we have the possibility to work with the climatology, which is not existing for the Antarctic. So one reason, again, to use more snow measurements. So yes, we are currently developing a new version of the Cryosat processor for the Antarctic, but we are not right now there that we have a product ready available. We have some comparison data sets for selected time periods, yes, but there is not a complete time series of the Cryosat now. But I hope to have that during this year.
What is the value of having thickness data in the Antarctic? I mean, the Antarctic is a bit different to the Arctic in the sense that most of the sea ice in the Antarctic goes every season, doesn't it? I mean, it goes down from about, 20 million down to about 3 or something like that. So is there as much urgency, imperative to have thickness data in the Antarctic?
Yeah, if we are able to compare thickness data in the Antarctic over longer time periods, we get an idea of the ice production, of the salt flux, for example, into the ocean. So if you have a large variability in thickness, a lot of melt and a lot of freezing again has a different impact to having a rather constant ice thickness over a long time and just melting it outside the Antarctic region.
Thank you very much. Are there any other questions?
I'm Nevin from the Arctic Sea Ice blog. I have a question for Dr. Nicolaus regarding snow depth on the ice compared to previous years. Was there more snow on the ice because of the cyclonic activity from the Atlantic?
I don't know, and because the unfortunate thing is that this great coverage of snow buoys in the Arctic we had last winter, we haven't had before. So there are just no comparable records in that amount over the last years. We have some buoys since 2012, as I said, but they are not good enough to make a larger scale comparison as this. So I think the way to do that right now is to use our buoys and to compare that with satellite algorithms that are currently under development and see how they perform, and then use these satellites to come up with larger scale estimates.
Okay, thank you. And I have one question for Dr. Dobrinin.
Yeah.
You talk about coastal erosion.
Yes.
Have you also looked at possible disturbances to the halocline due to increased wave activity?
Not yet, but it's one point what we are going to research, and so we're thinking about now. Maybe you heard about so-called Arctic amplification. It's a propagation of the water from the North Atlantic into the Arctic, and of course the water in the Arctic will be replaced by the water from the North Atlantic. But it happens probably on the larger scale as I show here. So we are not doing it now, but we're thinking about it.
Okay, thank you.
I have a question here from Catherine Yex from Science Nordic. What does an ice-free Arctic mean for the Gulf Stream and climate in the region?
She didn't specify which speaker was for, so whichever one of you wants to take that.
Can you please repeat your question?
What would an ice-free Arctic mean for the Gulf Stream and climate in the region?
Well, I will say the other way around, because what we have, the impact of the North Atlantic, for instance, in the Arctic, it's because of the Gulf Stream. And, well, that is consequences of the changing the water temperature, for instance, in the North Atlantic. And I cannot say something. I don't know about how the current will be changed in the future.
I mean, maybe one thing we can still add to that is what we do see if we look into these changes of Arctic sea ice, and if we go even to more extremes, is that we do see a change in the atmospheric conditions, how the patterns, the exchange between energy and water vapors that are changed from the high latitude to lower latitude, so that we have more convection that way. So that might also then in the end have an impact on or an interaction with the ocean, the Gulf Stream having also a north-south connection. But I think right now, at least for me, the atmospheric connection is more clear than the ocean link.
Thank you. Are there any other questions?
Luis Lidón from the Spanish news agency. I'm not a scientific reporter, so my questions are more general, like why the Arctic is warming faster than other regions, and what kind of impact would have an ice-free Arctic for the Earth in the next decades? Thanks.
You haven't said anything.
Yeah, so the Arctic is warming stronger than the rest of the world due to something called Arctic amplification, and that's a result of the fact that the Arctic is ice covered, or the land is snow covered, and the Arctic Ocean is ice covered, and so that makes it very bright. And so when we see any changes in the coverage, snow going to green land or brown land on land, and the ocean going from bright white to a dark blue ocean, we see large changes in the heat absorption of solar light, and so that has a big impact. And so if we have small changes that open up open water or open up currently snow-covered tundra to absorbing more sunlight, then we enhance that initial warming that led to that change. And so that's why we're seeing the changes in the Arctic most extremely. And that has a lot of impacts, both back on the climate, because we're absorbing more heat into the climate system, but also in the Arctic it has a lot of impacts on the ecosystems, the animals that are adapted to living in the snow-covered Arctic. Shipping companies might be able to cross the Arctic if we have continuous open water conditions in the summertime, and many other impacts.
I can add to the shipping. So it's a lot of studies now that it looks like we will have the better conditions for the shipping in the Arctic because of the ice is going back. But actually, if we will not have ice, we will have waves, and the waves can have a significant effect also on the winds of the ships velocities, and it can be not maybe it will be not quickly to cross Arctic somewhere over the North Pole, but it's maybe more efficient to get the old waves along the coastal line where the waves will be not so high. So it's a point to investigate as well for the future.
Yeah, but I think it's really important to point out that this is already happening now. This is not only something that might happen with the complete loss of the ice. So I've just attended the Arctic Science Summit week a few weeks ago in Fairbanks, and then somebody living in one of these coastal communities in Alaska really stood up and said, yes, I mean, it's not only your argument to motivate your science, but we experience this change already now. We do have the coast that get eroded. We do have less fast ice to work on, to travel on, and to live on. And for us in the more mid-latitudes, or like sitting in Vienna, I think it's more an indirect effect, like having more extreme weather conditions, these things. But it's already happening in the Arctic right now, and there's quite a lot of people living in the Arctic, probably more than we would expect here.
Okay. As a question for Alexandra, what's your assessment of how the models are performing now? Because they still don't seem to capture very well the observational data, do they? I mean, I remember back in 2007, and everybody was shocked by what happened, because CI seemed to step out so far from what the models were saying at the time. But even now, today, they still don't seem to quite capture what is going on.
Yeah, so the newest generation of the models is doing better than the ones that we had in 2007 when that first really extreme sea ice extent happened. And there are some of the models that are capturing the observations. So what I showed, the red line, it was within that envelope of the many blue lines. And what we've really become, really realized over the last couple of years is that large impact of internal variability, which makes it very hard to compare these climate models with observations. Even over these long 35, 38-year timescales that we have now, we're finding that this internal variability has a big impact on trends. So over that observational period, we actually, with the CMIP5 models, can bracket all the CMIP5 model trends can be explained entirely by internal variability from the CESM model. So we can't use that, for example, to exclude some of the models. So in a way, we're saying we're kind of capturing the observations now, but there's still definitely room for improvement in the models. But I think overall, there are some models that are doing reasonably well in simulating the important large-scale mechanisms for the sea ice loss. And what they're telling us is that this internal variability is just making predictions very difficult. So just like we can't predict the weather for Christmas of this year, they're telling us we really can't narrow down the year we'll see an ice-free Arctic or Arctic with only 3 million square kilometers of sea ice. That we really have an inherent uncertainty in the system. And I think in 2007, we weren't really as aware of that yet, that this internal variability can be so large and can both counter the forced response, but it can also go into the same directions, and that's when we might see these very large drops of sea ice that some of the model simulations were showing, where within 1 year you could lose 2 million square kilometers of ice in aerial extent. And that doesn't mean necessarily it's all gone, it just gets pushed together more or spread out more, and that's why we can see this large variability. So I think overall the models are definitely improving, and there's some that are doing better than others for sure. But I think we're on the right track on kind of looking at what we're going to see in the future.
Yeah. What's the observational data saying currently about the advection of heat into the Arctic? I mean, there was talk about a lot of warm water, particularly coming in at depth in the Arctic. Is that still happening?
Yeah, and we can clearly see that if we look at the Arctic sea ice coverage in March now. Like, we see that impact from the warm Atlantic water in the Barents and the Kara Sea, what Marcel was showing as well in the sea ice thickness. We see that in the aerial coverage as well. And so that has having a big impact, especially on that Atlantic side of the sector. And so I don't know if you have any more to say.
Sorry, can I just follow up? Because I mean, that one of the concerns going forward, and Mikhail could probably answer this question, is that if you've got more wave action on the surface, you've got the potential for more mixing, haven't you? And that warm water can then come up.
Yeah. So
and
basically,
drive more melting. Yeah.
Yes, what we call surface waves, it's only visible on the surface, but the nature of the waves is three-dimensional. So you do have an impact from the waves up to down to maybe 200 meters, depends on how big the waves are. And that's true, yes. We have also the additional mixing due to waves. And of course, if you will have ice replaced by the waves in the Arctic, you will have more mixing, and probably the mixed layer depth on the Arctic will be different as now. And that can have consequences for the heat uptake, or basically for the exchange between the atmosphere and the ocean.
More human activities in the Arctic, like with new shipping routes or exploiting oil or something like that, is going to accelerate the decline in the ice in the Arctic, or there is no possibility that human activities has any impact on that. Thank you.
Sorry, I didn't understand it. What was the question?
If we get more human activities like shipping within the ice-free Arctic.
So I know of one study where we looked at, I wasn't directly involved, but colleagues at NCAR looked at the impact of soot from shipping companies going through the Arctic on Arctic sea ice, and there they did not find a significant impact of that one particular thing, just from the increased shipping. And I'm not aware of studies that show an impact of that. On the ecosystem, we might expect more impacts there from pollution, especially from potential oil spills.
Yeah, I mean, maybe other aspects. So I think we are just right now, it's a process to build kind of the baseline, because a lot of these measurements like soot or like the impact of wastewater that ships might bring in, and they might transport species in and out, there haven't been these observations before. So we need to first have a baseline measurement in order then in a few years to say if that has changed. And how much that will change, I think this is very much an economic question. So there is more potential to do that shipping, but I think it's not a very easy question to answer how much of that shipping will be realized. If that's something that's really in the end commercially interesting, or if that's just an option. I think there are too many parameters that come from different sciences than from what we do with our ice observations.
Bob Berwin, freelance journalist. Dr. Dobrynin, following up on Neville's question a little bit in the mixing, what are the implications for the start of the freezing season from this mixing and more wave action? It looked like on some of those charts that you're still sort of projecting that the ice will start to reform at the same time.
Well, until the end of this century, we will still have the winter time. So it's only the difference that the summer will be extended to the 7 months. So the winter condition maybe not that will experience not so large changes in comparing to now. But in the summertime, the effect of waves, it's of course only one effect, and you have to consider that mainly it's going to from the global warming. So you will have the different conditions in the summer as now, the differences between the air temperature and the ocean temperature, and we also expect that the exchange of the heat between the atmosphere and ocean will be different. And on top of that, you can have also additional mixing due to waves. So that needs some more investigations and to do some more modeling study to answer that exactly. But definitely we will have other mixing scheme in the summer in the future as now.
Maybe I would like to add one thing to that point too, because if we look back into our thickness data that we have from 2012 after the record minimum, I think there are two competing processes, and you could argue well for both. You can see we have more melted water, we have more fresh water. It's more easy to form sea ice because we have a lot of open water. But we also have much more heat stored in the ocean in that open water, which that would make ice growth slower. And what we finally saw was that the winter 2012-13 had rather small ice growth rates compared to other years. Then only afterwards, in then 13, 14, 14, 15, then we had much more ice formation.
Hi, Robert McSweeney from Carbon Brief. I'm just following the point that you made, Mikhail. The graph you showed of the 7 months ice-free by the end of the century, is that your result specifically, or an existing one?
That is the results from one Earth system model that's also used in this CMAP5 experiments. If you're familiar with it, it's based for the IPCC report. That's the results projected by one model.
So is that 7 month number, does that take into account these larger waves, or would those larger waves potentially make that even longer?
No, that simulation not taking account any interaction between the waves and ice. But that's one point what we also can mention here, that due to higher waves, the ice is going to be, the ice breaking will be also different. You can expect that you will have more ice breaking due to waves. And this picture that I show in the beginning of my presentation, that's a typical picture for when you have the impact of the large or long waves from the North Atlantic, from swell, it's going into the ice. Maybe it can propagate into the ice up to 200 kilometers or something like that. And the ice, the whole ice field will be then rocked by the waves.
So do you expect that that 7-month period could be actually bigger than that once you take into account the waves?
The bigger in comparing to what?
The length of the ice-free period by the end of the century. Will it affect how, will it start earlier and finish later because of the waves?
Can we maybe open this plot? First slide. Which one? The first one. This one. Yeah, I go to full screen. So I can probably not answer your question right now, but because the starting of the season, it depends also on the region. So what you see here, it's a polar region, including the some part of the North Atlantic. And that is why the ice coverage here is not 100%. It's not only Arctic, it's also a part of the North Atlantic. So from that plot, if you will consider only the ice maximum, it is still in March and April. So I think the starting of the winter season will be probably the same.
Yeah, I wasn't sure if it was good to ask, but what the heck. Dr. Dobrinin, what about the East Siberian shelf and the methane clathrates in them? Did you look at maybe increased methane emissions, natural, from that? Or is that another subject entirely?
So I would like to invite you to my poster today, and
okay.
You can see there's some. So we cannot answer this question now, but what we are doing, we analyze the forcing factors that can lead to seabed erosion or coastal erosion. But that is only the first estimate, and so the models are not so far.
Thank you. Are there any additional questions? No? If not, we'll finish here. The next press conference is on the historical responsibilities and climate impact of the Paris Agreement, and it starts at 1:30. And until then, you are more than welcome to approach our speakers to have interviews either here or in one of the interview rooms that we have available. Thank you very much. And I should just mention that the Alfred Wegener Institute provided not only a press release, as did the University of Hamburg, but the Alfred Wegener Institute also provided images that are available at media.egu.eu/documents. Thank you. Thank you very much for your presentations.
Thank you very much.